assort your drawers or almirahs, you assort it in a particular fashion that you will keep one kind of dresses on one side, you will keep one kind of stationery on one side, one kind of books on one side. So depending upon the behavior or the nature, you will place them together. Like when you assort your home library, you will put all the chemistry books together, you will put all the physics book together, you will all put your mathematics, English together. I mean, they will be like one by one. So there will be a particular place where you, in which particular form in which you will arrange them, right? So is the case with periodic tables. First of all, atoms were known, and then we studied about atoms, and then their properties were now studied, right? Now you know that atom developed over a period of time, but the first atomic theory had come already in 1800s. So simultaneously, whatever atoms were discovered till that time, unka properties were also studied simultaneously. Supposedly you get something in your hands, the moment you get it in your hands, you try and explore it as much as you can, right? So Dalton, when he gave his atomic theory for certain elements which were known till that time, soon after that there were other scientists who started to study about their properties. Okay, that is what we will first see. As you know, I always talk about the history first. So in the history of the modern periodic table, the very first thing that we talk about is that 1800s, you know, Dalton gave his atomic theory, and simultaneously the structure of the atom was quite, the scientists got quite familiar with it, the entire world. So during the 19th century, chemists began to categorize the elements according to similarities in their physical and chemical properties also. But first physical. Physical is what you actually can visually check out, right? Then basically they were like put together, and when they were put together, they found that it could be arranged in a particular fashion. Like for example, first of all, in 1829, now you look at the year. You know the atomic structure very well now. Look at the year. So in 1829, maybe because the atom structure was now had started to develop. In 1829, Dobereiner gave his triad. Okay, his triad was like A, B, C elements put together. Some 3 elements were put together, in which the central one had the average atomic weight of the other 2. This is something that you have done even in your last class, right? So not going into the details of that. So we'll just quickly jot down the years one by one. Like lithium, sodium, potassium was there. So sodium had the weight similar to it was the average of the weight of the lithium and potassium. Then you have the other examples: chlorine, bromine, iodine. You can just note down these examples for your memory's sake. The very first time in 1829, because you know about the atomic theory, so I am not going into the details, but I will relate whatever we are going to do in periodic properties along with what we have done before. Okay? So in 1829, Dobereiner, I'll just check the spelling. In 1829, Dobereiner talked about the triads, and when he talked about the triads, some of the triads were lithium, sodium, potassium. Then he had put chlorine, bromine, iodine, that's like already mentioned on the slide, and then we have calcium, strontium, barium. These triads, you know, that's a group of 3. So and you have the central atom, so having an atomic weight. So basically what was the initial criteria? It's like if one thing gets suddenly discovered, the entire world runs after it. It's like following the herd at times. So it was based, his classification was primarily based on the atomic weights, and then whosoever actually thought of putting these elements together, he followed the criteria of atomic weights only. So they actually felt that this periodicity will come from the atomic weights of the elements which were known till that time, correct? So after that, what we had was in 1863 it mentioned about the Newlands. This is also something that you have done before, right? Newland law of octaves. Now before that, let me just talk about 1862 also. In 1862, you had a scientist with the name of A.E.B. de Chancourtois. Okay, now what did in 1829 Dobby gave his group of triads, that was according to the atomic weights. Okay, so this was also followed till almost 1862 when Chancourt-Toyce had replaced whatever he had till that time or whatever was known till that time according to increasing atomic weights, because he felt that these atomic weights, if they are arranged in an increasing order, probably you can get some kind of a periodic table. So his periodic table was a cylindrical kind of a periodic table. So you can just note it down that his was a cylindrical periodic table, but not was really very successful because the chemical properties were found to be a little different. And then came the Newland law of octaves in 1863, where he came across another new kind of a behavior of these elements when they are arranged. He found that the properties of the eighth element are similar to that of the first one, and the name octaves is given because of the, normally it's either sa re ga ma pa dha ni sa, so sa and sa is like the same, or it is do re mi fa sol la ti do. So do and do are like same. So basically the first and the eighth elements have the similar properties. What he suggested was that if they are arranged in some kind of an octaves, then the properties of every eighth element are similar to that of the first one. Okay, you can have a look at these people just like that, so that you know that they had done a lot of work, and they grayed their hair working all throughout for us. Next slide. So in 1863 we are talking about the Newland law of octaves. Acha, what were the problems with the Newland law, Newland's periodic table that he had actually given? The problem was it was only applicable up till calcium, that was like one. The other problem was also that he did not give any scope for the newer elements, right? That was also one of the limitations of his periodic table. And then in some of the cases the positioning of the elements was also not properly fit, right? That was also another thing. This was like the Newlands this thing, and here you can actually now check out that they were like somewhere in the formation. You all have gone through the actual periodic table, but they were somewhere close to the actual periodic. They were trying to get towards the actual periodic table. The point was to get something in such an order that the moment you look at it, you are able to classify that these all elements belong to one class and the others belong to the other class. So slowly, steadily, this was what was to be studied. So his, again, I told you this thing before, that like earlier, whose hypothesis was not widely accepted? When we talked about the quantum theory, whose Planck's hypothesis, because Planck stated that you can have discrete form of energy. I hope you remember the atomic structure. You're going to give a test on it today, right? So what you have is, you have the jumping of the electron from one level to another level. So he talked of the quantum packets, that the energy can happen only in form of discrete, when in classical it's like continuous. So again, whenever like a new theory is given, it is not taken with a very welcoming nature. It is always checked up for its various applications. Got it? So first, when triad was given, the thing was like it had very few elements were known till that time. Who gave the triads? Dobrina. And then after that, Chancourt-Toyce is like not very well known. It's not a very well known name because he talked about some periodic table which was also again not accepted. And then after that, in 1863, Newlands was famous. Why? Because every eighth element, this was like kind of a new behavior. Every eighth element was found to be similar to that of the first, with exceptions, because it was applicable only till calcium. Then there was no scope for the newer elements to be discovered, because there were still many. You cannot just think it's an infinite world. There is always a scope of the discovery of the newer elements. So there was no place kept for the newer elements. And then after that, again he did not, you were supposed to keep some, maybe the newer element has some place in between in between two elements of the periodic table. Then in that case the entire thing gets shifted, right? So that kind of an arrangement was not made by Newland. So that was like the law of octaves. Then See, that is what, just look at it. What did he do? I told you whenever a new discovery is made, it is how do you make it public to the entire world? By publishing it in an international journal so that people can actually. So, see what happened when he did this classification, he was told that it was as arbitrary as putting them in an alphabetical order. People told him इसमें कुछ खास नहीं किया आपने. There is nothing that special about it. Law of octaves, he applied the law of octaves to the elements which were known. So he was told that there is nothing special about it. So again, what now you understand this language? His paper was rejected. Rejected means that you have a publishing house, you have your journal. I have discovered something, now I will send that paper to you. You will go through that paper, and if you found it worth to be published, then only you will communicate it further. Do you get the meaning of that? ठीक है? This is like out of the course. I mean, generally telling you that if at all you come across any new thing today, the only thing is don't keep it to your heart and share it with your friends. What you have to do is, your responsibility is to share it with the scientific community. And how will you do that? By publishing a paper. So it was rejected for publication by the Chemical Society. So it was not accepted. Then after that, what we have is like after the law of octaves, we basically in 1868, Lothar Mayer actually gave a table which is similar to the modern day periodic table, and he observed change in the length of the repeating patterns. Okay, I can just talk about it. What was like in 1869, then you had Mendeleev's periodic table, which is like very well known. What do we have here? The slide that we just didn't cover was like his law of octaves failed beyond the element calcium, because then they were like not every 8th element was like not following the first one. The properties were just not similar. And then would his law of octaves work today with the first 20 elements? If we can just check that out, if every 7th element is finding it out. So these are some questions that you should think, how close they were to the modern day periodic table that we know. Okay, and then let me tell you, after Newland, so Newland was like the law of octaves, and he followed the law of octaves to give his periodic table. Then in 1868, before Mendeleev, Lothar Mayer actually arranged all the elements which were known according to their lengths. So this was like a newer concept. Till now, what was being followed? Basically, the atomic weight was given the priority, and then in this case, atomic weight along with certain properties were added up here. He gave preference to only atomic weights, Dobrina. Then Chancortois also arranged it according to atomic weights, and he gave a cylindrical kind of a periodic table. So the name cylindrical is related to Chancortois. Whatever name you is like the most complicated. Alright, then you have Newland, he gave the law of octaves. That was like again based on atomic masses along with certain properties. So properties were also related now. But here in case of Lothar Mayer, he gave a new angle to it, that he arranged the elements according to their atomic lengths. Length means you are talking about size. Basically length is like the radius or the diameter. You talk about the length of the elements which were known, and he arranged all the elements according to the atomic lengths. Okay, so this was like a newer angle. But problem क्या हुई मेयर के साथ? Before he could actually communicate his paper or publish his paper, Mendeleev gave his periodic table. Got it? So the moment you do something, you should immediately make sure that it comes before the world. What happened? Before he could actually talk about, because his was like a little close to the modern day periodic table, and then soon after, because research takes time, he must be continuously working on them, and soon after in 1869, Mendeleev talked about the organization of elements according to their increasing atomic mass. So again that mass pattern was being followed. Atomic mass, mass plus other properties, and then again atomic mass. So he got missed in between. Getting the point? So this is how it happens, and then he arranged it according to atomic mass, and then what we have is like Mendeleev gave his atomic periodic table. And when he gave his periodic table, do we have a question? He is what I'm actually talking about. What we have is, at the same time, what I'm saying in Lothar Meyer, he published his own table of elements organized by increasing atomic mass, but he actually talked about the atomic lengths as well. He not only took the, because mass was like a basic criteria, but he also gave it a new angle by talking about the atomic lengths. Next. Okay, the elements which were like, some of the elements which are known as are like not absolutely clear. Then in the next slide what we have is, both Mendeleev and Meyer, they arranged the elements according to the increasing order of the atomic masses. Both left, what was one good point, last time Newland did not give any vacant spaces. So both left vacant spaces which were found where some unknown elements could just fit in. So they left vacant spaces in between. But why is, now you know the answer to this question. Why is Mendeleev called the father of the modern periodic table and not Meyer? Because who came up with their results first? Mendeleev. So naturally that's like one of the reasons. And he stated that atomic weight of an element caused it to be placed in a wrong way, then weight must be actually wrong. He actually do not go into the details of this. He basically talked about the arrangement in terms of atomic masses only. And what he stated was, he gave his periodic law, which stated that the physical and the chemical properties, learn it right here, right now. What did Mendeleev state? That the physical and the chemical properties of the elements are a periodic function of atomic weights. Basically, this is the most important thing. Till now, everybody was arranging it only according to the atomic masses. Now, Mendeleev related both the physical and the chemical properties and gave this law. Law is something which is by and large applicable to majority of the, to almost 99% of the things which are known related to that. So he stated that the physical and the chemical properties are nothing but a periodic function of the atomic weights. This was by and large the law that was given by Mendeleev, and the father of periodic table is Mendeleev only. And after the discovery of some unknown elements, like, let me tell you, scandium, gallium, germanium, these were like scandium, gallium, germanium, these could be placed easily later because he named that them as Ika boron, Ika aluminium. So he named them as Ika. He stated that there may be some elements which were discovered actually later, some unknown elements which he actually tried to find out. He left places for them which could be successfully substituted. So whatever he found could be successfully substituted by elements like scandium, gallium, germanium. So you had the Ika names with them. So that means their properties could be related, correct? And then after Mendeleev, and remember that he is the father, okay? And just go through it, that what is written on the slide. However, in spite of Mendeleev's great achievement, the problems were still there, because newer elements were continuing to get discovered, and as newer elements were getting discovered, what we basically had was more and more atomic weights were like determined, because newer elements were like meant that they also need position in the periodic table. If you are resorting and putting all the atomic, if you are resorting and arranging all the elements together, then in that case the newer ones can pose a problem to your arrangement, because if suddenly you have to put something in between, it will cause a chaos. So that kind of a problem was there. So this is what caused chemists got the point, that even when you arrange something and I ask you to start it right from bottom again, it will cause headache. So it was something of that sort. Now this is all something that you had done before. Then the modern day periodic table was actually given by Henry Moseley, who observed regularities in X-ray spectra of the elements. Henry Moseley actually observed regularities in the X-ray spectra. Now you know spectra. X-ray means that which region are we talking about? X-ray region. You remember the entire electromagnetic series now? So the moment I say X-ray means I am talking about some frequency or wavelength which is beyond the visible range. Right? You remember what is it? Like you have cosmic rays, gamma rays, X-rays, UV, visible, IR, and then you have micro and radio waves. So all these regions have a particular wavelength. So he observed the X-ray spectra of elements, and he found that when a graph was plotted, this was like Moseley's findings, he found that when a graph was plotted between root of frequency, where this frequency is the frequency of X-ray, nu of frequency versus the atomic number, it could be found that it comes out to be a straight line. So he actually stated that atomic number is more important than even the atomic mass. So this was kind of a breakthrough. Everyone was somehow, some way or the other dependent upon the atomic mass. So he was the first person to talk about the atomic number. He stated that atomic number was more important than the atomic weight. And his law also goes in like the modern periodic law is what it states that the physical and the chemical properties of the elements are a periodic function of the relative atomic numbers. Got it, all of you? Because this is the modern periodic law. The modern periodic law states that all the physical and the chemical properties, because after knowing about the atom, what we are interested in is knowing about the physical and the chemical properties. And he stated that, the modern periodic law states that the physical, repeat it with me, the physical and the chemical properties of the elements are a periodic function of relative atomic numbers. Clear? This was the modern law. Otherwise, what was the Mendeleev law? Everything is just the same. It was dependent upon the atomic mass or weight. I hope you know the difference between mass and weight. Mass is like a constant entity unless and until the theory of relativity is applied to it, and weight is equal to mg. So, Moseley was also very greatly doing his work. He arranged his things according to the X-ray spectra. Now this was like a newer angle. Whatever new things come up, you try to use the latest technology. Now let's go through whatever you have done in 10th grade and whatever we've discussed till now. Who was the first one to talk about the arrangement of the elements which were known till 1829? Dobrina. He arranged it according to the triads. The problem at that time was like, you know, that the atomic structure was also being developed. So only very few elements were known till then. And the law of triads was like the central element has the average of the atomic masses of the other two. Okay? So this was it. And then thereafter we talked about in 1862, because the atomic structure was like known, was a little known till that time and was being developed. In 1862 again, all the scientists were talking about arranging the elements according to their masses only. Then Chan-Cortois gave some kind of a periodic table which was a cylindrical one but not a very successful one. He again was dependent upon the atomic mass. Then we talked about in 1863, soon after, Newlands gave his law of octaves, and his table was arranged in such a fashion that the properties of every 8th element, but again he was dependent upon the atomic mass factor, but now he had started to study about their properties also, because here we were talking about the atomic mass, here also they were arranged according to the increasing atomic masses. And then in 1868, I am telling you, Lothar Meyer had already started in accomplishing his research, which was based on the elements being arranged according to their lengths and atomic mass relation with the atomic masses. So length was also taken as an important criteria. Length means we are talking about the size. Clear with it? So size. And then thereafter in 1869 another table came up which is given by Mendeleev. Now there were like many plus points of the Mendeleev's periodic table. First of all, there was a Mendeleev's periodic law which was given. What did that state? It clearly stated that now accept this fact. Law is like something which is applicable to all the elements which were known till that time. What did it state? That the physical and the chemical properties of are a periodic function of their atomic mass, weight. You can talk about both. And then after that, what were the benefits of the Mendeleev's? First of all, many elements were known till that time, so they could be arranged. The properties were found to be similar of the elements which were grouped together. Then it also kept place for the of the undiscovered elements till that time. Okay, all this and more is what you've done before, and some of them could be successfully placed. Some of them could be successfully placed very well in the a periodic table, as he named them as Ikaboron, Nicosilicon and things like that, and then they could be relatively replaced by them. Just go through the names once, okay? And then there is a question here, what is relative atomic mass? Relative atomic mass is generally like whenever you check up the mass, you always take it in relation to something. Like you have the hydrogen having a mass of 1 atomic mass unit, that is considered to be 1/12 of the mass of carbon. So relative means whenever you are comparing it with something else. So that is why we call it a relative atomic mass. Otherwise it means as good as the normal atomic mass of any element only. Yes. No, Mayer's table was relating your lengths with the atomic mass. Mendeleev's table was like a little different because his was like talking about the physical and chemical properties and not just atomic lengths. You can compare the elements. I do not have the table for Mayer, but then they were like similar, because all of them were like approaching towards something which is more refined than the previous one. हमने जब atomic structure किया है, even in atomic structure we saw that slowly, steadily there were improvements in the atomic structure. So is the case with periodic table. First there were like some very few elements known, so they were grouped in 3, 3, 3 together. Then it was found that there were more of them, so then they were like arranged according to the octaves. Because by and large, what have you done? You do the Dobrynin's first, then you do the Mendeleev's, then you do the Newlands, and then you move on to the Mendeleev's and finally the modern day periodic table. But there were some little contributions from other scientists as well to be taken care of. Why do we talk of both of them together is the same case as why we talk about Schrödinger and Heisenberg together yesterday, for all those of you who were present. So here Mayer and Mendeleev's are also being talked together because they were actually trying to construct some kind of a periodic table which was much more refined than the previous ones which were known. Okay. Chan-Cortois table was based according to the elements which were known till that time according to increasing atomic masses. Mass, I mean here also let's talk about, this was atomic weight, this was also atomic weight, this was atomic weight with properties, and this was like atomic weights and atomic lengths, and here you have the physical and chemical properties related to the atomic mass. Okay. Then we talk about Moseley. Now Moseley gave one of the tables which is now refined as the modern day periodic table, because for the rest of them there is a lot of change. If you compare the Newland law of octaves and this one, there is a lot of change. So that way this change is there. Then in the next case, while Moseley was like actually discovering his periodic table, he was made to cut short because he was sent as a foot soldier to the World War I. And then when you go for a war, Either you can actually fight or you can do research. So research had a stoppage at that time. So his career was like kind of broken there as a scientist. Got the point? So that ways whatever he could discover was like more than sufficient. And then today you know that we have the modern day periodic table. I will just show you the modern day periodic table. And here what we have is like Seaborg. I am talking about this scientist because you should also be knowing about the newer versions now. Modern day periodic table was almost given like it was also the long form of, similar to the long form of periodic table that was given by Mendeleev, but Seaborg then newer elements now have new place in the periodic table and they go on to get arranged. Seaborg, he actually discovered 10 new elements in 1944. He moved 14 elements out of the main body of the periodic table. You know, recognize these. There are, if you look at the periodic table, there are some elements which are placed at the bottom. Those are the lanthanides and the actinide series. So he was one of those. And what is the special feature about the scientist is that during his living tenure, I mean during his life itself, one of the elements was named after him, Seaborg. There is an element named after him, that's Seaborg. And he actually stated by saying that this is like the biggest achievement, even better than getting a Nobel Prize. Otherwise, if you get acclaimed or for some prize after you are gone, then what's the point to that person who actually did it? But we should still cherish all of it and more. Then he was like, I told you that he was the person who actually got an element named after him. And thereafter, I think now we can just talk about the periodic table and have a look at the periodic table. There is another presentation. So in the meantime, just go through all the elements that we've just talked about. This one, periodic properties. Now see, when we talk about here, I would just have a quick look at it. See, now look at the basic structure of the periodic table. The basic structure of the periodic table revolves around, the basic structure of the periodic table, where's the duster? The basic structure of the periodic table is like, now look at the board, all of you all. I'm just roughly placing it, okay? I'm not making it. All of you have seen this table, right? This is not that of a building, but rather that of a modern day periodic table, where you have whatever is like red like this are your groups, okay? You get that? Whatever is red like this are your groups. Then you have whatever is red like this are your groups, fine, and whatever is red horizontally are your periods, okay? Now these are your periods, and then you have groups, first group, second group, and then you have third, fourth, fifth, sixth, seventh and eighth. We'll just talk about how they are placed. Now this region of your periodic table is known as the S block. This region is known as your P block, and this one is known as your D block. Now the names that are given to these blocks are according to the outermost shell which is getting filled. You already know how to fill the atomic, all of you all know how to write down the electronic configurations. So these names are given according to that only. So when we have a look at the periodic table, we can just discuss them quickly, right? Now we have already talked about the development of the periodic table as it is. We know that elements of the same group will have same chemical properties, because right from the beginning itself the target was that whatever is arranged in the same group should be having same properties, some similarity in their sizes or some similarity which can be related in such a fashion that they can be taken up together. Later it was found that there were some scientists who also studied chemical properties. How were the chemical properties studied? Say if you have three elements known, A, B, C, D, okay. If A is forming A2O3, because even the scientists during the development of the periodic table, they studied the properties of these elements by reacting them chemically with hydrogen and oxygen, and then the hydrides and oxides which were formed were taken up and clubbed together for their properties. So this forms your chemical properties as to how is it reacting chemically with oxygen. So if this was forming A2O3 and some other element was also forming C2O3 and this was forming say BO2 and this was forming DO2. So now you know that these two will be placed together, BO2 and DO2, because they have some kind of the same kind of chemical properties, such that the oxides which are getting formed have the same formula, and A and C could be grouped together. Got the point? So here remember that this is not just a child's play, but then there were many chemical properties which were studied. Properties are not identical. Identical as in they are not exactly the same. They may be different for each of the elements because each of the elements has an individual identity. Then now if you look at it, this was like as it was getting developed. See, these marks actually show the times when these elements were discovered, because slowly steadily elements were getting discovered and then they were like plotted, they were grouped together. Now Dmitri Mendeleev and Lothar Meyer, they independently came to the same conclusion. This is what we are talking about, and they kind of developed their modern day periodic table also accordingly, about how elements should be grouped, and some kind of grouping had already been established. Now here I am talking about it again, all of you all know, but then because you are just beginning to do the periodic table, very first thing that right here right now you should be doing. So please look up and get up to the call. Now here what you have is all these are known as groups, and when you move from left to right they are known as periods. They are also arranged according to the increasing atomic numbers, because what is the modern day periodic law? That the physical and the chemical properties are a function of their atomic number. Yeah, they are a function of their periodic function of their atomic number. So you have hydrogen and helium, that forms the first period. Hydrogen and helium, that's the shortest period. That question is also asked very vaguely in one of the papers. So you have hydrogen and helium in the shortest period, that is like the first one. The second you have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. These are the first 10 elements that you know. Now here in this case, first group means you have only one main shell, that is 1s1, 1s2. Now you get 1 and the second shell now. What is this? 1s2, 2s1, 1s2, 2s2. So now your 2 has started getting filled. So remember that principal quantum number also represents your period. Okay. So now here this will be 1s2, 2s, 2s2, 2p1. So now it's still 2, but the subshells of 2 which are getting filled. Clear with that? And similarly you have the last one, let me just come to it. This is 1s2, 2s2, 2p6. So fully filled. So this is your second period. Then we move on to the third one. Sodium is 1s2, 2s2, now third period. So you know the third principal shell will start getting filled up. So it will be 3s1, 3s2, 3s2, 3p1 and so on till 3p6. Okay. So remember that it is like the electrons are getting added up to the same shell only. This you can remember. Like what is common when you are talking about the periods? When we are talking about the periods, we are talking about the same shell. Okay. And as we move from first period to second period to third period, it is like one shell is getting added up. Okay, so now it's like first period done, second period done, third period. One more thing that you must have observed here is that when you talk about the configurations, it is like 1s1, 2s1, 3s1, 4s1, 5s1, 6s1 and so on. You do not remember the atomic numbers of all of the elements which are there on the periodic table. About 114 may be mentioned here, or we will check up another periodic table that I must have put ahead of this. In this case what we have is, remember that all these elements, even if you do not remember their atomic number and you remember them group wise, then you can write down the configuration. Why is this the S block? Because only S is the valence shell which is getting filled. What is the valence shell? It is the outermost shell. Speak up. It is the outermost shell. So in this case, which one is getting filled? 1s1, 2s1, 3s1. So generally for the first group, the configuration is written as ns1. Clear? For the first group, the configuration is written as ns1. For the second group, it is written as ns2. And then we move on to the p block straight away. I'm sorry. For the p block, it is np1, np2, np3 and so on and so forth throughout. Okay? np1, and remember that ns2 is already filled for all of these. That we have p getting filled now. So that is why, because p orbital is getting filled here, all these elements form a part of p block. And the last is like special one, because in this your p is fully filled. In this case your p is fully filled. And when you talk about the p fully filled, that means we are talking about the noble gases. These all are a part of your noble gases. And let me tell you, these noble gases were initially known as the inert gases. That is because at that time they were found to be forming very less number of compounds, or rather negligible amount of number of compounds, because it was found that these noble gases are, these gases which are like helium, neon, argon, krypton, xenon, radon, they have the outermost configuration as fully filled. And you know that fully filled orbitals are already very stable, very highly stable. So the one who is already stable would rather not interact. That element would just stay as it is. It would just say that I am not interested in interacting. So they were not found to form compounds with oxygen or hydrogen till that time, till a particular time. So that is why they were known as inert. Inert means something that doesn't react. But later it was found, no, that these gases are also capable of forming compounds, and therefore these gases are also known as these gases are also found to interact with other elements to form compounds, and that is why the name was changed from inert to noble. Clear? Then this central one, you know, this is 21, 22, 23, the numbering goes like that till almost 30. Now you remember, I hope you remember, hi, he, li, bi, bo, ka, na, o, fa, ni, and then you have so, ma, alsi, fo, sulfur, chlorine, argon, potassium, calcium. Then you have 21 to 30. What is it? Skr, tai, ver, kra, man, fi, ko, ni, ku, zn. Right? You all remember that? Now, I mean, there is no need to remember beyond that group period wise. Groups will now be more important. Why? Because the outermost configuration is important. And you know that when I talk about this D, what is the configuration here? 4s2, 3d1. And then you have 3d2, 3d3, 3d5, 4s1, 3d5, 3d6, 3d7. Tell me? 3d8, 3d10, 4s1 and 3d10. So here you have all these elements a part of which block? D block, because D is getting filled here. Clear with that? Because in this case, so this is like the 3D series. 3D because it's like forms some kind of, you know, you have 3D here, then this is known as the 4D series and this is known as your 5D series. Is that clear to everyone? Now look at the periodic table. I am giving you exactly 30 seconds to go through it. Remember that this is S, that is P, the central one is D. Remember that the electronic configurations are of the valence shell is the same throughout in a particular group. You call them periods in this fashion horizontally, and when you look at them vertically they are groups. And what else do I want to tell you is that lanthanides and actinides are something which are placed outside the periodic table, and where F block or the F is the valence shell which is getting filled. And you know F can get filled up from 1 to 14. Maximum number of electrons that F orbital can accommodate is 14. So remember that. So just go through it in just about 30 seconds and just memorize all these things here, right now. Answer the questions that I ask you now. Which is the shortest period? I hope 30 seconds are over. Do you need more time to just go through? Sure? Take another 15 seconds to have a look at the periodic table, because this is what is going to remain with you throughout chemistry. Clear? Okay, shortest period is first period. What are the elements? Hydrogen, helium. Which is a noble gas amongst the two? Helium. What is the outermost configuration of hydrogen? Which of the two elements can be solved quantum mechanically? Hydrogen can be solved quantum mechanically. Can helium be solved? No. He plus can be solved. Remember that. Okay, now the next question is, how many elements in the second period? 8 elements. Okay, and then what about the third period? How many elements in the third period? Okay, and these second and third are also shorter in comparison to the rest, right? Because for the rest you will have 10 of the D block elements also coming in between. Then what we have is 4 and 5, you know, are generally the long periods only. You have the 4 and 5 as the long periods. You all can see that. And then the sixth period has again inner transition elements also. The sixth period, now this was like first, second, third, fourth, fifth and sixth. Now if you look at the sixth, it has lanthanides and actinides, and because they are placed inside these are transition elements. I told you what is this, which block? D block, also known as transition elements. Now inside these transition elements you have hidden lanthanides and actinides. So those are known as the inner transition elements, because they are inside the transition elements, and the properties are also can be compared. As you move ahead in chemistry, we will see that their properties are also kind of studied. They can be studied along with the D elements only, with their behavior getting affected because of the presence of the D elements. So those are the inner transition elements, and here you have the seventh also having the inner transition elements. Now let's talk about the groups. What is the configuration of the outermost group here in the first case? 1s1. What about this one? ns2. You know that? Now out of these, just remember that the elements of the first group are known as the alkali metals. They are known as the alkali metals. Why? Because alkali are like they indicate the formation of strong bases. Like for example, sodium forms one of your strong bases. What is that? Sodium hydroxide, NaOH, right? So they form alkali. Alkali is basically a basic compound. So you have alkali. The next group, that is the alkaline earth metals. Okay. Then the third group is basically your group of the boron family. ये जो सारे ऊपर है ना, they are considered to be the head of the family because you can easily remember their electronic configuration. Alright, and if you can remember their configuration, the rest of the family is going to be the same with an increased period. And remember, you should be now able to write down the electronic configurations for any of these elements, and I will tell you how. So then in that case you will have, this is the boron family, then you have the next as carbon family, and the next is nitrogen family, is also known as pnictogens. Nitrogen family is also known as pnictogens. In the spelling you have P is silent. P is there, which is like silent. So what you have is pnictogens. These are the poisonous compounds forming elements. Nitrogen family is also known as pnictogens. These are the poisonous compound forming elements. If you want an example, say nitrogen forms nitric acid. Alright, then there is another acid which is like picric acid. So all these acids are like quite poisonous in nature. So, and the gases, like you have nitrogen dioxide, you have N2O3, NO, all these are like your major pollutants. So basically in that case you remember that this nitrogen family is known as pnictogens, which means poisonous compounds forming elements. And then you have the oxygen family, which is known as that of chalcogens. Alright, oxygen, this is your nitrogen family, then your oxygen family is known as chalcogens. Chalcogens are those compounds which are the ore forming ones. So chalcogens means they are the ore forming compounds. Alright, they are the ore forming compounds, ORE, you know, all know ores. Then you have fluorine family, which is, all of these are known as halogens. One special feature about halogens are like they have the outermost configuration as NP5. Tell me the configuration. What is that? NP5. Okay, and NP5 means that they need only one electron to complete their outermost valence shell electronic configuration. And the last one is like fully filled, and those are known as the noble gases. All of you all know that. Let's memorize the periodic table right here, right now. Ready? Ready with me? Now here, you know the first, second, third period that you can remember. Hydrogen is known, that's like a part of the shortest. So here you have, remember that there is no association or link for it to anyone, but it's like Lina, Kabr, Karb, Se, Farar. Alright, you will remember that. You have to remember, this is lithium, Na is sodium, potassium, rubidium, cesium, francium. Because you have to memorize. I am just devoting 2 to 3 minutes so that you can learn this periodic table here itself in about 5 minutes time. What is it? Lina, Karb, Se, Farar. So that's like easy. This is like the first group with the electronic configuration as NS1. That is important. Now if I ask you, what is the outermost configuration of cesium? You can tell 1s1, 2s1, 3s1, 4s1, 5s1, 6s1. So the outermost configuration for it is 6s1. And before that your all elements may be like either fully filled, they will be like filled. And then you know the Aufbau's table. You know how to construct the Aufbau's table that we do. Do you want me to do it again? Sure. So then in that case you can fill up the rest. You know S can accommodate a maximum of 2 electrons, P can accommodate a maximum of 6, D can accommodate a maximum of 10, and then comes again your F, which is 14. You remember that F will start getting filled up only from the 6th and the 7th period. Before that you will not fill up your F at all, and according to the Aufbaus also you will see that. Done with the first group? All of you all? Stronger. Next one is group 2, where the outermost configuration is NS2. So what is that? बीमा का स्ट्रोंशियम 12. Repeat it strongly. So what does it mean? Beryllium, magnesium. Remember, Ma is not Ma, that's Mg. Alright? Magnesium, calcium, strontium, barium, radium. Done with it? We've done B marka strontium bara. That's like done. Alright. Then here we come on to the group 3 of the major. After S, your P gets filled first here in this case. So this is NP1 Bal Gaintal. Bal, Bengan Aloo also is Gajar in Thela. Gajar in Thela. ठीक है, that is also fine. Bengan, aloo, gajar in Thela. So the way you remember, that's absolutely fine. Then this is like college students get some problem is what I remember, and even carbon, silicon, germanium, tin, lead can also be remembered. Alright, and then you have for this and there are other ways also. So please remember, for those of you who do not remember, there is another way of remembering it, which is even a better one. New Zealand, Pakistan, Australia, sub by. किसी को भी भाई बनाओ, पर the point is that you should be remembering it for your exam, from your examination point of view. So it should be remembered, and the outermost configuration of the topmost head of the family is already known to you. So if you know the top, then you can do it for the others as well. If you have it for antimony, because this is nitrogen, phosphorus, arsenic, antimony, bismuth, the names also need to be remembered. ये नहीं है कि एक बार कुछ किया इसको learn बस खत्म. So this is like antimony and bismuth. Then this is very easy, जो आपने कभी करना नहीं है, लेकिन आप इसको learn करने के point of view से बोल सकते हो, उससे टीपो, उससे टीपो. नहीं, उससे टीपो is like okay, but then you never gonna follow it because nobody helps you in the real world and you cannot rely on anybody else except yourself. So that's usse tipo. And then this is like halogens that I remember generally like that. What is that? Fluorine, chlorine, bromine, iodine, astenine. Alright, repeat it. Fluorine, chlorine, bromine, iodine, astenine. And then the last is like your Nobel gases, which are helium, neon, argon, krypton, xenon and radon. That also can be remembered. I am giving you exactly 1 minute now to remember the periodic table. To remember the periodic table from group 1 to group 8. Do it quickly. Done? Shall I ask one by one from all of you all? Done? Let's start from there. Can you please repeat the lines to remember clearly group wise? Yes, because this is very important and you need to remember the periodic table. Please take it off. So let me just ask one by one from here. First group. No, it's okay. Whatever you remember. Helena ki Rab se Faryad is one. Whatever you like. Helena ki Rab se Faryad or Lina Karb se this is not Kabr, this is Karb. Karb se farar. So whatever you remember. Okay. So first group done. Second from here. Stand. Tell me. No. Sit and tell me. What will this be? बेटा माँ स्कूटर बेटा मांगे कार स्कूटर बाप राजी. Not the correct language, but then please remember it. Okay, there is either I remembered it faintly like बीमा का strontium 12. So that's like one way, thoda sa related to chemical way. But otherwise, as I've been told by your friends only, it is beta mange car scooter baap razi. All right. Okay. So second group also done now. One last time for the. This is like one last time that we're revising this. For this, it is Pengan, Alu, Gajar in Thela. Okay. This is boron, aluminium, gallium, indium, thallium. So that I do justice to my chemistry also. Alright. So again, Bengan, Alu, Gajar in Thela. Then this is like Kashi Gaye Shankar Prabhu. Alright. Remember that Kashi is for C. So Kashi Gaye Shankar Prabhu. Or carbon, silicon, germanium, tin, lead. Carbon, silicon, germanium, tin, lead. After saying that Kashi wala line, please remember those elements also once. Alright. What is this SN? Shankar? Tin. Please, this is very important. More than your, no, God is also equally important. But then, you have tin. And this is PB is your lead. Alright. Then you have New Zealand. New Zealand को बनाओ, नेपाल को बनाओ, New Zealand, Pakistan, Australia सब बाय. Okay? New Zealand, Australia, Pakistan सब बाय. Means nitrogen, phosphorus, arsenic, antimony, bismuth. Okay? And then you have उस से tipo. ठीक है? And then you have fluorine, chlorine, bromine, iodine, astenine. And helium, neon, argon, krypton, xenon. Fine? Last half a minute to just go through it again. And then I'm just putting down the general configurations for see, basically there is one thing. This is your group 1, group 2. 3, say we start with our transition elements, right? Because this is your third group ideally. So this is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then your actual, the one that I'm saying group 3 is your group 13, 14, 15, 16, 17 and 18. The only thing is when you actually, these groups are actually linked to your S block because the properties go in synchronization with it. Your transition elements, so that is why in many of the books you will write it, find the groups named as 3A, 3B, 4A, 4B. So because they all can be grouped together in some properties which are linked to say the number 3. Why? Because the outermost configuration in all these cases is NS2, NP1. So what are the valence shell electrons? 3. What is boron? Boron is 5. See, boron is your atomic number 5. And when you take the K element shells, you remember this or forgotten? So 5 you used to place maximum of 2 electrons in K and this becomes 3. So this grouping, when I call it group 3 for Bengan, Alu, Gajar and Thela, that's like boron, aluminium, gallium, indium, thallium. So now in that case, what you have is, if I am placing them in group 3 means I am talking about the number of valence electrons. What are valence electrons? These are the electrons in the outermost shell. जो भी कुछ outermost shell में होता है, that is called valence electrons, and the shell is known as the valence shell. So remember that this is also numbered as group 3, 4, 5, 6, but otherwise these are 13 to 18. These are from group 13 to 18. So when you minus 10 from them, subtract 10 from each one of them, you actually get the number of valence electrons, valence shell electrons in each one of them. Okay. Then for the transition elements also, you can actually write down the configuration. And how can you write down the configuration for say groups 3 to 12? 3 to 12 means I am talking now from scandium to zinc. I am talking from scandium to zinc, and remember that in D block you have 3D series, 4D series and 5D series, and then you have 6D also now, and there are many newly discovered elements which have also come up. So you have the basic n-1D can get filled up from 1 to 10 and ns 0 to 2. The outermost configuration for the D block is n-1D 1 to 10, ns 0 to 2. You can apply it to any of the elements to check it also. क्योंकि इससे हो सकता है नहीं समझ में आ रहा हो, ये generalized है. If I take up the example of say manganese, what is it? 25. So what is that? 25 means I know this will be my 4s2 is already filled and this will be 3d5. So you see that it will be D 1 to 10 will be according to the positioning in which group. अगर first group third group में है तो it will be D1, fourth group में है तो D2, fifth group में है तो D3 and so on. So you can find that out 3D5, लेकिन जो next number है that will be one number higher and S2. Got it? 3D series में totally 3D भर रहा है, 4D series में 4D is getting filled, 5D series में 5D is getting filled, and when that gets filled, the s orbital is generally one higher with one higher principal quantum number. Okay, got it? For 31, for 21 to 30 as it is, you know. And then we have for say lanthanides and actinides. Please note it down for lanthanides and actinides also. Lanthanides are like 4Fn 5D 0 to 1 6s2. This is like the general electronic configuration for lanthanides, and for actinides it is just one step higher, because actinides क्या है उसके just नीचे. तो अगर आपको पता है कि this was like your 3D, 4D and now 5D series. Lanthanides is in which series? 5D. Lanthanides is in 5D series, right? And then your actinides are in 6D series. So you get it, in lanthanides your 5D is the one which is getting filled. And क्योंकि actinides उससे एक step ही नीचे है, तो उस केस में हमारा क्या हो जाएगा? This will be 5Fn 6D 0 to 1 and 7s2. तो अगर lanthanides का electronic configuration याद हो गया तो actinides automatically आ गया. Okay, because that is just one step ahead. That is in accordance with the laws of fully filled and half filled also, and the most stable structure. Like, because for copper, what do you have for copper? It is 3d5 4s1. But otherwise, what is the configuration? It is 4s2 here, right? Otherwise 4s2 gets filled first. So that is why we set up a range. And तभी for D elements we have set up a range as ns 0 to 2. Because अगर कहीं वो देखेगा कि fully filled होने के chances हैं या half filled होने के chances हैं, then it will borrow it from S and take it. So goes the case here. Alright, it will be filled according to that only. And here the main thing that is getting filled is like your 4F. So basically it starts from lanthanide, so it is like 4F1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and goes on till 14. Got it? So then we can actually talk about some important features, the typical elements that we've seen. One thing is that there is something which is known as the bridge elements. Keep looking at the periodic table only. Please focus on the periodic table only. What are the bridge elements? Is the periodic table clearly visible to everyone? because I am standing close, I can watch it, look at it clearly. Now see, now here what is this? There is like some kind of a diagonal relationship. I tell you, diagonal relationship means that the first element has properties similar to the second element of the next group. So in that case, lithium will have properties similar to that of magnesium, beryllium will have similar to that of aluminium, boron will have properties similar to silicon, and so on. This goes on till almost your nitrogen to sulfur. Clear with that? This is like known as, the elements of the second periods are also known as, that is why the bridge elements. These are also known as the bridge elements, the second period. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, they are generally put as the bridge elements also, because they show a diagonal relationship with the, diagonal is like because their properties are found to be similar with the properties of the second element of the next group. Now what are valence electrons? Some very basic concept. What are valence electrons? They are the electrons in the outermost shell. And what is the valency then? Valency is also something that you've already done. Valency can be actually defined as the number of electrons or the number of electrons that are required to either to make valency is something that is like a number which makes sure that your outermost electronic configuration can be fully filled. So sometimes, like for oxygen, I hope you remember the previous, this is like now your 8th grade concept. Like for oxygen you have K, L, M, N shells, right? How do you actually write down the configuration for oxygen? That's 8, so that will be 2, 6. So what are the total, the number of valence electrons? 6. The number of valence electrons are 6. How many electrons are required to complete the outermost shell? 2. So the valency in this case will be the maximum number minus the number of valence electrons. So in this case that will be 8 minus 6. So valency in this case will be 2. And that too, you generally write down the oxidation state as minus 2, because whatever takes up is taken as minus and whatever is given out is written as plus. Alright, now if I talk about sodium, what was sodium? It was 2, 8, and you have in M shell also 1. So in this case, rather than accepting 7 electrons, iski valency will not be 7, but its valency will only be plus 1, because it will be willing to give away 1 electron. So whenever for KLMN you had done, whenever 4 or less than 4, that valency is equal to the valence electrons. Yes, when you have the number of valence electrons to be 4 or less than 4, then in that case that itself is the valency, because it is easier to give 2, 3, 4 electrons, right? But when it goes more than 4, as in case of oxygen, then in that case the valency is the maximum number of valence electrons minus the valence electrons. So the maximum number that can come in L is like 8. So 8 minus 6 means it's 2. And let's check it out now from your 11th grade point of view. What is the configuration of oxygen? It is 1s2, 2s2, 2p4. So what are the maximum number of electrons that can come in the p orbital? 6. Maximum that can come in p is 6. तो इसको और कितने चाहिए? ये p4 है. p4 means 1, 2, 3 and 4. So it needs 2 more electrons to fill it completely. So that is why it will have an oxidation state of minus 2. Got it? Clear with that? So this is another thing that you need to remember, that valency. Now what will be the valency of the noble gases? The valency of the noble gases will be 0. Why? Because their outermost orbital is like completely filled. Their valence shell is completely filled. Okay. Then there is another thing that we can talk about, 3 things in this periodic table: metals, non-metals and metalloids. Now you know what are metals? Metals are They are electropositive in nature. The ones which are like have the tendency to give electrons are your metals. The ones which generally have the tendency to take up electrons are generally your non-metals, and the ones which have a behavior intermediate to those of metals and non-metals, then it is called known as metalloids. Now generally let me tell you here in this case, when you have talk about the S block, they are generally metals. As we move from left to right, the metallic character decreases, because now you know why will the metallic character decrease, because the tendency to take up electrons will be more. The one which give away electrons are electropositive in nature and they are metallic in nature. Now the ones which have a tendency to take up electrons are electronegative in nature and they will be known as non-metals. So non-metals increase on towards the right side of the periodic tables, and whatever is like in between lie in the range of the metalloids. Clear with that? Clear to everyone? Metals, non-metals. So let's look at it further. Next slide. We've seen the development of metallic. See, this is what Mendeleev's predictions were. Now we are already on to the modern day periodic table. We've started learning it up. But before that, you should just go through from your examination point of view. Just go through. Like we started from Dobrino and then we came on to Newland and then finally to Mendeleev and then now modern day periodic table. Remember the Mendeleev's periodic law and the modern periodic law also. And this is how he actually studied. See, when somebody studies, what we basically have is, see, all these properties are actually memorized. What are those properties? Those properties are checked, not memorized, they are checked. Like the atomic weight, density, you know, all of you all know about atomic weight. So all these scientists used to do something which was very elementary. So even you all can venture into such kind of things in future. Atomic weight, density, specific heat is that something that you will do in thermodynamics. Melting point, you all are aware of melting point. So all these properties were basically studied and all these properties were compared. So when we talk about the physical and chemical properties, they are not just 1, 2 properties but so many of them. Okay. So here, yes. Can we have the previous slide again? So what we have is Mendeleev's prediction was on money. That's like goes into the history. So there's a story that I'll tell you once we complete up with the atomic structure. Alright, otherwise that will also take some 2-3 minutes time. Next slide. What we have is now there are some important concepts that need to be rationalized. Periodic table set ho gaya. But let's study, and we've seen that all the valence electrons, the outermost configuration now fits in. Now you see the importance of the atomic numbers. कैसे? पहले तो आपने atomic structure देखा. Atomic structure से you get to know the number of electrons and the behavior. One thing, ये हमने last chapter में देखा. अब एक बार you know the number of electrons and how they are filled according to Aufbau's principle, Hund's rule of maximum multiplicity and your Pauli's exclusion principle. ये सारे rules लगेंगे in filling up your electrons in according to the atomic number. Then your atomic numbers, once they are known, the outermost electronic configuration can be known. If your outermost electronic configuration is known, you can place them group wise. S1, S2, P1, P2, P3, P4, P5, P6 and D1 to D10. This is what we had seen. Now you relate the two chapters that we had done. So those configurations can now be arranged in your periodic table. Now in your periodic table again, diagonal relationship is satisfied till almost nitrogen and to the next one, sulfur. After that it faints a little, fades. Okay, then done. Then what we have is, we were talking about the properties. They are like arranged. Now once you have arranged them and learnt them and you know now the configuration of each one of them, there are other properties that need to be memorized. Now look onto the board. The properties that need to be done are, the very first one, please remember, the very first one is your size. Okay, atomic size. How can you size? Radius, uh, or you can have even sometimes the ionic radii are compared. All these can be related to one another. Then you have, say, ionization energy. And please remember ionization energy right here, right now, that it is, first you listen, memorize, and then write yourself. Look up, all of you all. Remember, these are now new terms which you need to be very absolutely thorough with. You must have done it from the top last year also. What is ionization energy? It is the energy required to remove the outermost electron. So, if somebody needs to be pulled out from somewhere, you need energy to pull out that person, right? So, what is ionization energy? It is the energy required to remove an electron from the valence or the valence shell, from the outermost shell or the valence shell. Clear? Write it down yourself. What is ionization energy? It is the energy required to remove the electron from the outermost shell. Done? It is really very, very, very important. It is the energy required to remove the electron from the outermost shell. Then you have electron affinity, or this is also known as electron gain enthalpy. This means that when done with ionization, all of you, now look up. Now for electron gain enthalpy also learn it and then write it. What electron affinity is also known as electron gain enthalpy. It's one and the same thing. This is like the energy released when an electron is added. So remember the difference between the two. Ionization energy is the energy required to pull the electron, to remove the electron. And electron gain enthalpy or electron affinity is the energy released when an electron is added to the outermost shell. Clear with that? Remember that energy released is like different from energy that is required. It is like if suddenly I add up a new member to your class who is very much active, what will happen? The energy of the class will increase, and then what will happen? It will be released. So it is the energy released when an electron is added to the outermost shell. Then how are they different from electropositivity and electronegativity? Remember that electropositivity is the tendency of an element to lose electrons. It is the tendency. We are not talking about energy. Matlab, what is the capability of an element or it the tendency? Electropositivity is the element. Electropositivity is the tendency of an element to remove an electron from the outermost shell. Oh, sorry. Electropositivity is the tendency of an element to lose electrons. And that losing of the electrons generally happen from the outermost shell only. And then for electronegativity is the tendency of an element to gain electrons or attract electrons. Now there are doubts. What is diagonal symmetry? Diagonal symmetry is like when we move back to the periodic table. If you look carefully at the periodic table, say this was your periodic table, right? Okay, let me just talk about the first one. You have hydrogen, lithium, sodium, potassium, and then you have B, beryllium, magnesium. So the relationship of the first element of the group to the second of the next group, it's kind of a diagonal, right? The relationship of the first element of one of the groups is it's actually related. The properties of this are found to be strikingly similar Many properties are found to be strikingly similar to the second element of the next group, and this is known as the diagonal symmetry or the diagonal relationship. So this is diagonal symmetry. The next doubt that we have was in second and third group properties of elements are more similar with diagonal element or with the element after them in that group. No, it is only between these two. Diagonal relationship means that we are talking about the similar properties of the first element, that means of lithium with magnesium, of beryllium with aluminium, because there you have now for the P block you have. So this will have properties similar to aluminium. So it is not with the rest of them. The rest of them will have the properties which will be similar to NS2NP1 only. They will have properties similar to NS2NP1 only. Okay, and then the next doubt is why 12th group zinc are not considered as transition elements while all the other D blocks are. See, this is a very good question, because when we talk about the D block elements, let's talk about the D block elements, the 3D series ले लेते हैं. 3D आप सबको आती है, तो let's take up the 3D series. What is the 3D series? You tell me. Very good. अपने आप Zn बाहर भी हो गया. Now here in this case, all these are considered to be a part of transition elements, but zinc, then you have cadmium and mercury. All these three are not considered to be a part of the transition elements. You can answer the question yourself. Can you tell me the electronic configuration? D1, 3D2, 3D3, 3D5, 4S1, 3D5, 3D6, 3D7, 3D8, 3D10, 4S1, 3D10, 4S2. Okay, so for if this is 3D10, 4S2, this will be 4D10, 5S2, 6D10, 7S2, 3D4, no, 5D10, 6S2. Be careful, this will be 3D10, 4D10, 5D10 and 1S higher. Alright, so this will be 3D10, 4D10, 5D10. In the case of zinc, cadmium and mercury, the outermost electronic configuration of the D block is completely filled. So if it is completely filled, the behavior will be somewhere similar to that, not exactly to the noble gas, but then they will be different than the rest of the transition elements. Alright, the behavior will be different than the rest of the transition elements because they are fully filled and would rather not show the properties similar to the other elements which are partly filled d orbitals, because for all the rest they have a tendency to accommodate more d electrons. Here there is no tendency. This is like a very valid question, why zinc, cadmium and mercury are not considered to be transition elements. Then in that case you have to talk about their electronic configuration. What is the electronic configuration? Ns2, N-1, D10. For zinc, cadmium and mercury, it is 3D10, 4D10 and 5D10. Now because of the outermost valence shell to be completely filled, we do not talk about them to be a part of the transition elements. Alright, the next thing that we can actually talk about is, yes? What is the reason of diagonal relationship? I tell you, see, reason is like not there. We have arranged our now elements according to their chemical properties and physical properties being a function of their atomic numbers, which fits in exactly with other properties like length, ionization, energies. We'll just see. But so similarity, that's what the question is. So when we talk about about the similarity, it was found that now say supposedly you will say ye to second group wala is similar to the first group wala. So why is it placed here? It should be picked up and placed along with it because the properties are similar. The majority of the properties are similar to the second group. Let's compare lithium with magnesium, right? Let's compare lithium with magnesium. Now magnesium belongs to group 2 and lithium belongs to group 1. Now majority of the properties of magnesium are similar to that of group 2, but there are strikingly similar properties of this element with the element of the on the left hand side on the top, right. So now here in this case your lithium will have strikingly similar properties to that of magnesium. So that is why we checked this. Now this relationship was then checked for the other groups as well, and it was found that even beryllium had properties similar to that of aluminium. Okay, so this was again a trend that was set and fitting into the periodic table, so we let it be. Correct? And it may be because of the closeness in nature and the sizes. We'll just compare the sizes abhi. When we look at the periodic table, and when your sizes and your basically if your sizes are comparable, there are many properties which are similar, because on going from left to right you will see that the size decreases, on going from top to bottom the size increases. So they have their comparable sizes also. So one chemically from chemistry point of view reason can be atomic size. Okay, but otherwise do you get it? After arrangement it was found that this was again a trend that was set. Lithium being similar to magnesium, your beryllium being similar to aluminium, and so on.
Excuse me, ma'am.
What is the difference between oxidation state and valency? When you take the magnitude of the oxidation state, I would rather say that acts as the valency, because valency actually defines that the number of electrons that need to be given or need to be accepted to make the outermost shell completely filled, right, whichever is the outermost shell. And when you talk about the oxidation state, it is that state which is achieved once the element has got a configuration which is similar to that of the noble gas. Like for example, if I write oxygen, oxygen is 2s2 2p4, alright. But if I write O2 minus, then the configuration will be 2 minus, मतलब ये ले चुका है, it has already taken 2 electrons. So this is the configuration of O2 minus and this is the configuration of simply oxygen. So here you have the oxidation state, here you can talk about the valency. What is the valency of this oxygen? 2. What is the valency of O2 minus? 0. So I mean if you talk about the valency of O2 minus, it will be 0, but otherwise if you can relate O2 minus, you can say that 2 minus is the oxidation state and or 2 is the valency of oxygen. Got the point? So it can be just understood like that. How polarizing power affects diagonal relationship is something that when we talk about covalency creeping in. So we'll keep a hold to that question till we go further on. Okay. Transition elements are called so because their behavior is like in the transition, yeah, it is like kind of intermediate between the S and the P block, and their properties are like similar to acting as like in the transition cases. Like for example, there are many things that actually make them transition elements. One reason is that they have the d orbitals which are incompletely filled. Okay. Then second reason is that they actually form compounds of variable oxidation states. अभी तक आप oxygen की बात कर रहे हो which is just -2. It needs only -2. But when you talk about now because you've asked a question, her question is why are transition elements given the name transition? Now they exhibit variable oxidation states also. Like for example, you talk about vanadium. What is vanadium? Skertiver 23. What is the configuration? 4s2 3d3. So let me tell you the oxidations that it can display is like it can easily give 1 electron, it can easily give 2 electrons, it can easily give 3 electrons. The most stable will be +3, but it can show +1 and +2 also. Then ये S से भी रिलीज कर सकता है. Oh sorry, the very first would be, I'm sorry, the configuration is like, so it can show +1, +2. +2 is one of the most stable ones, right? But then if it loses this D also, then it will become even more stable, because then it will reach neon, then it will reach helium, neon, argon, sulfur, chlorine, argon. It will reach the configuration of number 18, right? So it will try to go towards that noble gas now. बात समझ में आ रही है? For D block elements, it is not just one oxidation state. So their properties are also like in the transition phase kind of. So that is why we name them transition elements. Now that I have talked about it, let me just complete it here itself. समझ में आता है तो ठीक है, नहीं तो just take a break and relax. So what you have is 4s2. तो 1 और 2 तो आराम से देगा, फिर 4s 0 हो जाएगा. तो आउटर मोस्ट शेल तो खाली. लेकिन inner most कौन सा? It was like filled. It was also not completely filled, so the next will be like +3. +3 में it will become 3d2. Then +4 में it will become 3d1. And +5 में it will become 3d0, 4s0. And the configuration will be similar to that of argon, number 18. Clear? So that is why. Why modern periodic table has a 3D structure? The modern day periodic table has a 3D structure so that there is a scope of addition of more and more elements to it, so that you can add elements from various directions. So presently known number of elements are around 118 or 18 or 19, 119. So in that case the newer elements actually keep coming up, and there is like a scope of addition and variation. Now another important concept. Have you written about electropositivity? What is electropositivity? It's a tendency to lose electrons, and electronegativity is a tendency to gain electrons. So basically electropositivity and electronegativity can be related to your bhook and pyas. It is only a tendency. Got it? It is a tendency. But once it gives, what is involved? Ionization energy to remove the electron. And when it takes up an electron, what is the energy involved? Electron gain enthalpy or affinity. That is the energy released. When energy is required, what is it? Ionization energy. When energy is released, it is electron gain enthalpy. Now another point is like effective nuclear charge. What is your effective nuclear charge? See, we have many electron systems now, and both are attracted towards the nucleus. We have talked about the shielding effect yesterday, right? Dekho, the charge would be like, if I say that there are 10 electrons, then the charge should be plus 10e. The charge should be directly 10 electrons. So charge on an electron is E, that is 1.6 into 10 power minus 19 coulomb. So straight away charge should be related to that. But you have a nucleus which has a positive charge. Atoms are considered to be electrically neutral. Why? Because the number of protons is equal to the number of electrons. ये तो बहुत elementary चीजें हैं जो पहले कर चुके हो. तो अगर मैं nucleus की बात कर रही हूँ, तो nucleus के आसपास there are electrons. Now 1s gets filled first, then 2s gets filled, then 2p gets filled. And you know that whenever an electron is added to the outermost shell, it will be facing repulsions from the electrons which are already present there. Alright? All of you all are aware of that? So it will face those repulsions, and that is known as the shielding effect. So because of that, the effective nuclear charge can be reduced than the actual nuclear charge. You getting the point? The effective nuclear charge will be different than the actual nuclear, because the nuclear will now face a different kind of a behavior. Now here, what is the nuclear charge depends on how the electron feels, depends on both the factors. Now here you actually, that's what it's showing. You have the nucleus here, then you have the inner shell electrons, and then you have the valence electrons getting filled outside. Precisely what I am talking about. Next slide. So what we have here is, if you have to calculate the effective nuclear charge, please note it down. The effective nuclear charge will be Z minus S. This is the formula for effective nuclear charge. Simple one. where Z you know is actual charge that you talk about, it's the atomic number, because your atomic number is equal to the number of electrons. That is equal to the atomic numbers. And S is your screening constant, usually close to the number of inner electrons. Screening constant होता है एक, screening by shielding constant or screening constant, which is close to the number of inner electrons. So the total number of electrons minus 1, it can be n minus. Yes. Okay? Yes, otherwise what's the point? Alright, so here what we have is, remember that the effective nuclear charge, you should just know the formula. The effective nuclear charge is Z minus X, S, where S is your screening constant. Valence, now I mean if we take an example, just think about which element's outer shell or valence electrons is predicted to have the largest effective nuclear charge. Think about potassium. There is a doubt, ma'am, in vanadium, why we fill 4s2 and 3d3, why don't we fill 3d5? See, that's again a valid question. We have chromium after vanadium, which has 3d4, 4s2. What we do is we take one electron and give it to 3d to make it 3d5 and 4s0. Now a very valid question is, if it is 3d3, so दोनों electrons of S can be given to 3d to make it 3d5, 4s0. That is done only in situations where there is pressure on the system as it is. Otherwise, energy, because of the energy considerations, it becomes very difficult to shift the electron from the 4s orbital to the 3d. Each transition involves energy, you all know that. Each transition of electron from one level to another level, it involves energy. So if I am talking about the shifting of an electron from 4s to 3d once, it in itself requires a lot of energy. Chalo, wo ho gaya, because we are looking for half-filled orbitals. Now for vanadium, even the second electron will have to be shifted now. Now the first electron must have faced a lot of repulsion from the inner shell electrons already, and now if you add second electron, the energy would be almost 10 times or more greater than the initial energy that was actually involved. So that will involve even greater energy. So एक electron add करने का still there is some scope, but the second electron is just very difficult from the energy considerations point of view. समझ में आया कि first electron का add करना, it in itself involves a lot of energy, and the jumping of the second, and first was easy because it was seeing that one electron, if it shifts from this place to this place, it will make it half filled. But there it is like two electrons, and two electrons cannot jump simultaneously, they will have to do it one by one, and if they do that, then in that case the energy does not support it. So that is why vanadium does not take up a configuration of 3d5 4s0, rather it remains as 3d3 4s2. Okay, then next, now here if I talk about the effective nuclear charge, now here just look at the effective nuclear charge. Then what is for chlorine? Chlorine is atomic number 17 minus, now what is the screening constant? Now देख लो, इसके अंदर या तो you can remember the k element shell concept. This is chlorine. What is it chlorine? 2, 8, 7. So what are the valence electrons? 7. Inner electrons कौन से हैं? बात समझ रहे हो कि electrons will be added in the outermost shell only. We are talking about the inner shell electrons. So your effective nuclear charge Z effective will be equal to Z minus S, where this S is almost equal to the inner shell electrons. So what are the inner shell electrons in this case? It will be in the n minus 1 level. So it will be 17 minus 10. ये बात समझ में आ गई? Very clearly, easily understandable. Or what you can do is, from your now understanding point of view, what is the electronic configuration of chlorine? 1s2, 2s2, 2p6, 3s2, 3p, 5. Now what are the inner shell? n minus 1 shell देखेंगे. What are you going to look at? You will be looking at the number of electrons which are contained in n minus 1 shell. What is n? 3. So you will look at shells only till 2. So 2 plus 2 plus 6. How many electrons? 10. So it will be the screening constant will be equivalent to 10. So your effective nuclear charge will be equal to 17 minus 10. Yes. That no 6 plus 2, 8 plus 2, 10. Inner, all inner. 6 plus 2 plus 2. I felt my maths is wrong temporarily. So now what you have is 17 minus 10. This thing is clear to everyone. Now you can check out for the others. Now look up here. Here now you have for oxygen. What will be your oxygen now? It will be 8 minus 2. Now for oxygen, let me just write it down. So then you will understand. What is your oxygen? It is 8. 1s2. This is your oxygen. 1s2, 2s2, 2p. N shell is the outermost shell. N minus 1 has only 2. So what is the effective nuclear charge here? 8 minus 2, that is 6. For nitrogen similarly you can calculate, and this equivalent sign means that because we are not taking exactly the screening constant but rather an equivalent, approximate values. So that is why it is 8 minus 2, that is equal to 6, and here for nitrogen therefore it will be 7 minus again 2, or the nearest or you can talk about the noble gas atomic number which is less than that number. जैसे मर्जी समझ लो उसको, समझ में आया? Then for calcium it will be 20 minus argon's atomic number. This is 7 minus helium's atomic number, 8 minus helium's atomic number, 17 अब argon से छोटा है और neon से बड़ा है तो 17 minus neon's atomic number. Got the point? लेकिन screening constant का मतलब समझो that whenever your electron is getting added up to the outermost shell, the valence shell electrons are facing repulsions from the inner shell electrons. तो उसकी वजह से effective nuclear charge is going down. Clear with that? So which of them have the highest nuclear charge? You can just check it out. Chlorine. ठीक है? But you should be able to calculate. अब ये नहीं है इसमें से 10 माइनस करें तो सब में से 10 माइनस करके देखोगे. You have to think logically. So that yes, you can see that effective nuclear charge is similar, but in this case we are relating it even to the screening constant. So just in case if you have the value of the screening constant, you should know that that should be equal to the Z minus the screening constant. Now what are valence electrons? You know those are the electrons in the outermost shell. And for main group elements, they are the electrons which are filled in DNF also, like I showed it to you. If you have 3D 4s2, the valence electrons can be considered as 2 also because they are the outermost shell electrons. So that is why plus 2 is also stable and plus 5 is also stable because there S will also be given and D also will be given off completely. And for transition elements, electrons in full F shells are not valence electrons. The outermost shell will be considered, whichever. You getting the point? That if you have 3D, 3, 4s2, what are the valence shell? What is the valence shell? 4s. And then you have 3D. So it is not like the KLMN concept, it is like 4s. You have to look at which is the outermost orbital. Next. Okay. So now here for the valence electrons, we've already discussed this. You can write down the electronic configuration and then check out the valence electrons. So in this case, the valence electrons are reflected like the total electrons in the outermost shell. Now here for arsenic, what is this? 3D10 is already filled, but we look at the 4. So the highest principal quantum number will be considered as the valence shell and the electrons contained in it will be your valence electrons. Then for this iodine also you can just look up whatever is reflected in your blue are your valence electrons, right? Now for the sizes All of you all have a picture of the periodic table before your eyes? You have it, not on the screen but before your eyes. Have it? Now in case of the periodic table, I am telling you one thing from examination point of view. ऊपर से नीचे जाते टाइम साइज इंक्रीज होता है, बाकी सब प्रॉपर्टीज विल डिक्रीज. On going from top to bottom in a group, size and related properties increase, the rest of the properties will decrease. And left to right in a period, across the period, the behavior will always be the opposite. Okay, this is the main funda of this chapter, that you have to remember that on going from top to bottom, there are atomic size and related properties will only increase. All the rest of the properties like ionization energy, electronegativity, electron affinity, and electronegativity, whatever you talk about, that electropositivity can be discussed, but then for the rest of the properties, what you have is, for the rest of the properties, they will all decrease on going down the group and increase on going from left to right. So what did I say? I talked about, just to begin with, periodic properties. On going from top to bottom, size increases and the rest of the and related properties will increase, but the other properties like ionization energy, electron gain, enthalpy will decrease. And on going from left to right, it will be the opposite, just the opposite of this trend. Related properties, I tell you. अब देखो, सब अपना periodic table, just keep it in your eyes, before your eyes, in the air, in your mind. It's there. Now when you go from top to bottom, you know that one shell extra is being added. Let's talk about the atomic size only. Let's talk about this question. It's like simple. The effective nuclear charge is like the charge which is actually contained by the atom in totality, and that is the atomic number minus the screening constant. And जो हमने screening constant लिया, they are nothing but that's equivalent to the inner shell electrons. ठीक है, वो inner shell electrons कौन से होंगे? That will be the total number of electrons in the noble gas which is lesser in atomic number than that atom. समझ आया? Z effective, the effective nuclear charge is equal to Z minus S. Z is the atomic number, वो तो जो भी atomic number है. What is your S? Your S will be that screening constant that refers to the repulsions which are faced by the inner shell electrons, and those inner shell electrons will be the ones which will be belonging to one shell less. मान लो if you are talking about the third shell getting filled, जितने भी second shell तक filled electrons हैं वो सारे will be your S. Okay? Now we move on to the size again. The question is now size. पहले बात करते हैं ऊपर से नीचे जाते टाइम increase क्यों होगा? Because what is it? Let's talk about Lena curve say Farrar. All right. What you have is lithium, sodium, potassium, rubidium, cesium, francium. Lithium is 2s1, sodium is 3s1, 4s1. In all these cases, you know, if lithium is, what is the configuration of lithium? Let's look at it like that. Because if you understand one property, let me tell you, all the other properties become very simple. From the mugging point of view, I've already told you atomic size and related properties will increase down the group, baki sab will decrease. And on going from left to right, it is opposite. So just remember one thing, the entire periodic table is yours. Okay, so now if I talk about the periodic table size, look onto the board now, onto the board. Now here what we have is, if I talk about lithium, sodium, potassium, rubidium. Let me talk about these two first. What is this? This is simply 1s2, 2s1. This is 1s2, 2s2, 2p6 and 3s1. Now here one full shell of 2 has been added up. So there will be an increase in size naturally because of one extra principal shell getting added up. So on going from top to bottom, what will happen? One extra shell is getting added up. So there will be a kind of, you know, and so much of repulsions will be faced by this electron. So naturally, because electron getting added up means आपके पास अगर 11 charge 11 electrons are here on the side, तो nucleus जिसके आसपास ये revolve कर रहे हैं उस पे भी तो plus 11 charge है. Nucleus also has protons. So basically when you have addition of shells, the first of all the effective nuclear charge is like a little lowered. Why? And the repulsions faced will be larger, and one basic important reason is extra shell means increase in size. But chemically अगर देखो तो लगेगा इलेक्ट्रॉन ऐड हुआ उसको अट्रैक्ट करके छोटा करना चाहिए, बिकॉज इतने सारे इलेक्ट्रॉन्स ऐड हुए हैं तो इसका चार्ज भी तो +11 है. So the size, now here in this case what happens, because the shell has increased, so the repulsive factors will be dominant over the attractive factor. ये थोड़ा थोड़ा समझ में आया. Main reason for increase of size on going from top to bottom is that you have addition of a new shell. So that means my size is increasing. Okay, got the point? Now size को relate कर दिया. Let me just relate another thing, that is ionization energy. What is your ionization energy? Energy required to remove an electron. तो इसका मतलब ionization energy will be maximum जब मेरे को remove करने के लिए मुश्किल होगी, right? तो अब मुझे देखो 2s1 is close to nucleus, right? Nucleus मतलब imagine that with positive charge. 2s1 is close to nucleus, so it will be very tightly held, right? Lesser electrons, lesser repulsions from inside, so it will be very tightly held. So in that case the ionization energy will be high, because मुझे ज़्यादा energy is required to remove the 2s1 electron. But अब 3s1 is like थोड़ा सा little far away from the nucleus, and then there are inner shell electrons also to repel it. So the ionization required will now go a little less, क्योंकि अब ये बाहर है उतना attractive force नहीं है जितना इसमें था. So it will be easier to remove the electron from the 3s shell. So that means as the size is increasing, the energy required to pull the outermost electron is less. So ionization energy is decreasing. समझ में आया? The ones who got tired of the class should now wake up now, because this is very important to understand the reasons. ऊपर से नीचे जाते टाइम क्या increase होता है? Size. Size क्यों increase होता है? Because of addition of shell. So तो top to bottom जाते टाइम it will be easier to remove the electron. That means energy required to remove the electron will be less. So then in that case the ionization energy will decrease on going down the group. ठीक है? और जितनी आराम से इलेक्ट्रॉन देगा तो इतना मतलब इसका see it would like to give electron. All these are electropositive in nature. Why? Because सबके पास एक एक इलेक्ट्रॉन है वैलेंस इलेक्ट्रॉन्स में. So all of them would be willing to lose electrons. So that means the tendency to lose electrons is more here. They are electropositive in nature. Okay, they are electropositive in nature. Now as you move down the group, the tendency to lose electrons will be greater and greater, क्योंकि वो दूर होता जा रहा है, so प्यार भी कम होता जा रहा है, तो it will just lose away the electrons easily. So then in that case you would say that the tendency of electropositivity also decreases down the group. So that would mean that the metallic character, now in this case, so, sorry, the tendency to lose electrons will increase. Sorry, in a flow. So what we have is, here it is closely held, so this will lose the electron a little with a lot of difficulty. But here, as the size is increasing, the tendency to lose electrons will increase. Okay, the tendency to lose electrons will increase because it is easier to remove the electron as it is. तो ionization energy तो हमने बोल दिया, ionization energy is decreasing down the group. अब अगर electron easily remove करता है तो the tendency to show electropositivity will increase. ठीक है? And अगर electropositivity increase हो रही है इसका मतलब metallic character is increasing down the group. So just in case if I just fumbled before, please last revision for this. Remember, on going down the group, size will increase, ionization energy will decrease. Metallic character will increase. So that means metallic character can be related to your size. Got it? So I told you atomic size and related properties will increase, baki sab will. So goes with your electron affinity also. Ionization energy हो गया. Now the main another third property that I talked about is electron affinity. What is electron affinity? All of you all tell me. It is the energy released when an electron is added to the outermost shell. Okay? Energy released when an electron is added to the outermost shell. So अब यहाँ पे electron मैं add करूँगी तो it will face repulsions from just 3 electrons. So in this case energy released will be sufficiently high because they will be like tightly held. So now as you add, so it is like quite difficult to add an electron here. Why? Because no, just wait. Here in this case, when you add an electron, there will be repulsions faced from many more. So the electron will not be very gladly accepted. देखो जितने ज़्यादा अंदर electrons होते जाएंगे उतना it will be difficult for the atom to accept another extra electrons. If the class gets completely filled, it will be difficult to accommodate more students, right? So therefore, अगर difficulty बढ़ जाएगी तो उस case में energy release would be very less. So then in that case electron affinity would also decrease. Electron affinity will be more when it is easier to add the electron. ये लिख लो. Electron affinity will be more ताकि कोई confusion ना हो. Electron affinity will be more when it is easier to add an electron. ठीक है? Electron affinity will be greater when it is easier to add an electron, and it is easier to add an electron when the inner shell electronic repulsions is less. And it is easier, समझ के लिखना, and it is easier to add an electron when the inner shell electronic repulsion is less. समझ में आया? तो इस केस में इलेक्ट्रॉन को ऐड करना कहाँ इजियर होगा, इसमें या इसमें? Li में. तो इलेक्ट्रॉन एफिनिटी ऑफ Li will be higher and for this will be lower and for the next will be even lower. So electron affinity also decreases down the group. This is from my understanding point. Another thing is, अब अगर मैं सीधा एक halogens की बात करती हूँ, fluorine, chlorine, bromine, iodine. What is the configuration? Np5. So is it easier to add an electron to them? Because they will attain full complete outermost shell configuration. It will become Np6. तो electron add करना easy है, मतलब electron affinity will be very very high. Electron affinity will be high when it is easy to add the electron. This is like for your understanding. This reason should not be cited otherwise. You can talk about the inner shell electronic repulsions. Okay? See the exact, now a doubt has come up, what is the meaning of the screening, what is the exact value of the screening constant? See, screening constant is just a hypothetical concept of the value of the number of electrons which are repelling the outermost shell electrons. And that inner shell electrons are equivalent to the screening constant. So that is why the exact value can be calculated experimentally, but otherwise that screening constant is approximately equal to the charge of all the inner shell electrons. Okay, now coming to the size again. Now look at the screen because the presentation is there. What you have is bonding radius, remember, is 1/2 of the distance between the two covalent radii. ये याद रखना कि अगर आपके पास H2 molecule है तो what will be the length of H2 molecule? It will be half of the length of H plus H. This is like more useful for heteroatomic molecules. What are homonuclear? Yes, when you have the same atom, and heteroatomic cases are the ones when you have different atoms. So here in this case, when you talk about the sizes, remember that the distance will be 1/2 of the distance of the two. just the average of the two. And this is what we are talking about, the general trend. Look at the periodic table, all of you. Periodic table को लिटाया हुआ है यहाँ पे. So what you can see in the periodic table, as you go down the group, size is increasing. And left to right की अब बात करते हैं. As we move from left to right, size will decrease. वो तो मैंने learn करवाई दिया, because on going from top to bottom, you know that the size will increase because of addition of shell. I told you the behavior left to right across the period will be different. So why will it be different? Just quickly look at it. Let's compare the second period of lithium. Okay. Then you have what? Beryllium. Sorry. This is what you have. Okay. Reason top to bottom का सबको समझ में आ गया? Top to bottom क्या होगा? One last time. Atomic size will increase. Ionization energy will decrease. Why will it decrease? Because it is easier to remove an electron. Electron affinity will decrease. Why will it decrease? Because it becomes difficult to add an electron. And metallic character will increase because the tendency to lose electrons will increase. Okay, and then if metallic character is increasing, means that your electropositivity is increasing down the group. But for the rest of the properties, it is decreasing. Okay, now here, lithium is what? Tell me the configuration quickly. 2s. This will be? Then this will be? What is the similarity in these? That the electron is getting added to the same shell. In सब में क्या हो रहा है? Electron is getting added to the same shell. So what you have is 2s to 2p3, 2s to 2p4, then you have 2s to 2p5 and 2s to 2p6. किसी को कोई शक for the electronic configurations? पक्का? Now इस केस में कोई एक्स्ट्रा शेल तो ऐड नहीं हो रहा, पर इलेक्ट्रॉन ऐड हो रहा है. रिपल्शंस होंगी, साइज बढ़ भी सकता है, लेकिन साइज डिक्रीजेस. Why? Because what is the effective nucleus? What is the number of lithium? It is 3. Because in some cases में 1s2 is already filled. 1s2 is already filled in all these cases. So what we have is 3, 4, 5, 6, 7, 8, 9 and 10. These are the atomic numbers, right? Now in all these cases, I see that the number of electrons are increasing. If the number of electrons are increasing, the number of protons are also increasing. तो न्यूक्लियस का पॉजिटिव चार्ज, अगर इलेक्ट्रॉनिक चार्ज इज -3, तो न्यूक्लियस पे चार्ज कितना है? +3. Now in this case what happens? As we add an electron to the same shell, it is easier for the nucleus to attract it even more. Okay, it is easier for the nucleus to attract it even more, and because of that attractive force, वो attractive force क्यों है? Because the effective nuclear charge is increasing. Effective nuclear charge कैसे देखोगे इस केस में? It will be 3 minus 2. What is that? 1, 2, 3. वही वो. I mean it will be 4 minus 2 and then 5 minus 2. Basically the number of valence electrons only. Then it becomes 4, 5, 6. So the effective nuclear charge is increasing. Nucleus का charge बढ़ रहा है and the electrons are getting added to the same shell, means it will have a greater tendency and greater power to attract the electron, and because of that the size will contract and it will decrease on going from left to right. For you it will be left to right. So it will be decreasing on going from left to right. Now the moment an extra shell gets added up, next period में जब हम जाते हैं नीचे top to bottom, तो next shell में जाते टाइम में तो electrons add हो रहे हैं, लेकिन उस टाइम में because there is an extra shell, that leads to an increase in size. It is just as if I am like talking and say punishing 7 students who are standing in a circle around me. Okay, if the 8th one comes, he will be the new person who gets trapped. So I will have a tendency to attract that person equally or punish that person equally well. So that attractive force is increasing because you have a tendency to interact with the first shell, which is like in the same shell. But the moment a person comes outside in the next shell, that may get hidden behind. So the effect of attraction will decrease. Say if you sit on the last bench, sometimes you lose track and you go in your own world to think about something else. That is because you have now created a lot of shielding constants. क्योंकि आप दूर हो गए हो, तो the attractive force has now become lesser. But if you keep clogging onto the first seat itself, then in that case there will be greater attractive force because of which you will catch the attention. Getting the point? So remember, when the electron is added to the same shell across the period, then in that case the effective nuclear charge increases, attractive force, electrostatic force of attraction increases, because of which size decreases. Okay? Size decreases because now the electrons are tightly held. ठीक है? Clear? Size will decrease on going from left to right in a period. अब अगर size यहाँ पे decrease हो रहा है और मैंने बोली बाकी सब properties उल्टा ट्रेंड फॉलो करेंगी, तो बाकी सब properties increase होंगी, पर justify करते हैं. If on going from left to right, atomic size is increasing, atomic size is decreasing. So then that would mean, I am saying that in this case now the nucleus is holding these two electrons strongly together. पहले से भी ज़्यादा strongly they are holding them together. So the energy required to remove the electron will be even more, right? To remove this first electron there was some energy required. What is that? In ionization energy. Now if it is tightly held, now effective nuclear charge बढ़ गया, same shell में electrons और tightly held हो गए, तो you require more energy to remove the electron. And if in case you require more energy, then in that case, then that means ionization energy will be more. So on going from left to right, because of tightly packed structure and effective nuclear charge increasing, you will find out that the what will happen? Ionization energy will now decrease. On going from left to right, the ionization energy will increase. Why will it increase? Because now they are tightly packed and you require more and more energy to remove an electron. Now let's talk about electron affinity. What is electronegativity? The tendency to gain electrons. And if the tendency to gain electrons increases on going from left to right, then that means it will take up the electron easily. And if the electron is taken up easily, your electron affinity will increase. Because when is electron affinity more? When it is easier to add the electron. Clear to everyone about that also? So on going from left to right, now you tell me atomic size will?
Decrease.
All of you all, it will?
Decrease.
What about ionization energy?
Increase.
Electron affinity?
Increase.
Why will the atomic size decrease? Because the effective nuclear charge is increasing and electron is getting added up to the same shell, electrostatic force of interaction increasing, attraction increases. So size decreases. You do not have to talk about the shielding effect here. Shielding is like it's shielding the nucleus and interact नहीं करने दे रहा उसको. But here same shell में जब add होगा, see if I am talking to 5-6 students around me in a circle, then I am interacting with everyone. If the 6th-7th student comes in the same circle, I can equally interact, right? But if that person comes outside, then that shielding will come into play. Got the point? So do not use the wrong word.
Can we say that ionization energy is also effective shielding effect?
We can relate it, but in some of the cases you will actually have to look at all the elements. सिर्फ कुछ elements को देख के नहीं, सबको देख के we can generalize a particular thing. Okay? Okay, now let's look at the presentation again. Now in our presentation, now you tell me on going from top to bottom the size? Because shells increases. And then you can talk about the effect that you were talking about. On going from left to right, size decreases. Ionization energy, on going from top to bottom, it will decrease. On going from left to right, it will increase. Okay. Electron affinity on going from top to bottom will again decrease, and on going from left to right, it will increase. And which will have the highest electron affinity? Halogens. It is easiest to add the electron to P5, because P5 will go into P6 to attain the noble gas configuration. So the highest electron affinity will be shown by fluorine. And then which is the highest electronegative element? फ्लोरीन, क्योंकि ऊपर से नीचे जाते टाइम डिक्रीज होता है और लेफ्ट टू राइट जाते टाइम इंक्रीज होता है. इट्स जस्ट एज सिंपल एज अ सिंपल गेम. सो व्हिच विल बी द मोस्ट electronegative element? Fluorine. Which will be the most electropositive element? That is in that case you will have lithium, sodium, potassium, rubidium, cesium. So cesium will be one of the most electropositive, because ऊपर से जाते टाइम नीचे electropositivity increases and left to right it decreases. So naturally, so that ways you get questions in your entrance examinations, which is the most electronegative, which is the most electropositive, which will have highest ionization energy, lowest electron affinity and things like that. So based on your understanding, periodic table आता है, you understand all the concepts, so you yourself can pick it up. You don't need to mug all these elements. This is the highest electron. Yes, you need to go through it once, because sometimes your understanding may be a little different. But after going through it, it is very important that you memorize them on your own. In the sense that understand, go through and memorize. अगर memorize भी नहीं किया तो सब class waste है. It is just a zero again. Okay. So bonding atomic radius tends to decrease from left to right across the row, and it decreases from top to bottom. Next. Generally, when you talk about the metallic character, we do not consider the radioactive elements because they have a tendency to decay. So then in that case, you have to look at the options which are given. They will not give you either the radioactive element would not be given, or the other thing will be like choosing. Let's look at the choices. We'll take up the questions now in the next class to have a more better look at it. What is ionic radius? See, ionic radius is something. This is another good question. We'll just come to this. Your question came at the right point. Okay, there was a doubt from one of the centers. What is ionic radius? So now see, sizes of the ions. Now remember that whenever a plus charge is gained, that means, अब आप खुद थोड़ा सा सोच के मुझे बताओ. If I give BE a +1 charge, okay, it was 4. What does it become? It becomes 3. And on the left hand side, your size is. Now here in this case, the size will be a little more. So, but in this case, we have to check up what happens on a +1 charge and what happens on a taking up a -1 charge. So, one thing is you can always relate it to the atomic number which is previously filled, and then you can relate it to the sizes and other properties accordingly. So, now one step ahead. The basic property is done with everyone. Now we move ahead with the size of the ions. See, the ionic size also depends upon the nuclear charge, कि उस टाइम पे कितना चार्ज है उस चीज पर. ओके So ionic charge depends upon the nuclear charge, it depends upon the number of electrons, and it also depends upon the orbitals in which the electrons reside. कि electrons जहाँ पे रह रहे हैं कौन से orbital में है, that is very important to know. You need to know the number of electrons and you also need to know the nuclear charge. Nuclear charge तो अब सबको निकालना आ गया है. So then we move on to the rest. Now here see, lithium is 1.34. When it gets a +1 charge, what happens? उसने अपना एक इलेक्ट्रॉन दे दिया. +1 का मतलब है it has given away its 1 electron. Lithium plus has now become 2s0. If it has given 1 plus electron, then it becomes only 1s2, which will be even tightly held by the nucleus. सो देने की वजह से जो बाकी के इलेक्ट्रॉन्स हैं दे विल बी टाइटली हेल्ड, और यू कैन थिंक ऑफ इट इन अ वेरी नॉर्मल फैशन. इफ द एटम इज गिविंग द इलेक्ट्रॉन, ठीक है, एक इलेक्ट्रॉन तो चला गया, वो बाकियों को टाइटली होल्ड कर लेगा. अगर टाइटली होल्ड करेगा व्हाट विल हैपन टू इट्स साइज, ताकि और ना कोई निकाले. यू गेटिंग द पॉइंट. सो व्हेन एन इलेक्ट्रॉन इज गिवन आउट it gains a plus charge. Plus charge means a cation is getting formed, and if a cation is getting formed the size is decreasing. That is what the value shows. Lithium has a size of 1.34 and these all sizes will be in angstrom only. So and what is the size of Li plus? That is equal to 0.68. Okay, and then let's compare some negative charge as well. Now oxygen has a particular size, ठीक है, उसने 2 माइनस इलेक्ट्रॉन्स, 2 माइनस मीन्स 2 और इलेक्ट्रॉन्स ले लिए. क्या होगा उन इलेक्ट्रॉन्स का? आराम से अंदर आने देगा एटम, आराम से आने देगा. क्यों आने देगा? आने देगा बिकॉज इट्स लुकिंग फॉर द नोबल गैस कॉन्फिगरेशन. बट द इनर शेल इलेक्ट्रॉन्स विल ऑल्सो शो repulsive effects. So whenever electrons are added the size is tending to now increase, क्योंकि अंदर से repulsion होगी. Getting the point? So then in that case the size will increase. So please take care of that. Now what are we talking about? If we are moving from the normal atom to a plus state, that means cation is getting formed. So the cation will have a lesser size. Why will they have a lesser size? Because एक electron चला गया, बाकी सबको it will be tightly holding the rest of the electrons even with that, because the effective nuclear charge remains the same. What is the effective nuclear charge of lithium? Z is equal to plus 3. Number of electrons were 3. 3 में से एक चला गया, कितने इलेक्ट्रॉन्स रह गए? 2. बट इफेक्टिव न्यूक्लियर चार्ज क्या रहा? प्लस 3. अरे दैट इज लाइक अ सिंपल थिंग. लिथियम के अंदर कितने? प्लस 3. बाहर से 1s और ये में 2s. जस्ट आई डोंट शो सच चाइल्डिश डायग्राम्स नॉर्मली. दिस इज लाइक प्लस 3 चार्ज. ये हमारा क्या है? न्यूक्लियस. ऐसे बना देती हूँ. This is your 1s, 2 electrons, 2s, 1 electron. Now lithium, it is lithium only when it becomes plus 1. So this is like lithium. When I show lithium plus, I will remove the electron. Now this electron is removed. अब कितने electrons रह गए? 2. Effective the nuclear charge, sorry, the nuclear charge is still plus 3. So then in that case now it will hold them even more strongly. Got it? Earlier this nucleus was taking care of 3 electrons. So maybe the outer one had the privilege to leave. So once it leaves, it attains a noble gas configuration which as it is stable. And then in this case, this plus 3 will hold the 2 electrons even strongly, which will lead to contraction in the size. So that is why cations will generally observe throughout a size which is less than the normal atom. Because after losing of 1, it attains some kind of a noble gas configuration. The nuclear charge remains the same and it will hold the electrons strongly. So K and K plus, K is 1.96, K plus is 1.33. So it was just a comparison of the actual experimental sizes. ये बताने के लिए कि cations का size is always lesser than the normal atom. And anions ka size is greater because now when the electrons are added up, they will face inner shell electronic repulsions because of which the size will tend to expand. So in case of anions, the size will increase. Clear? Then in that case, in case of Li plus, you will see that the effective nuclear charge will turn out to be equal to 3 minus 2 only. Then you will have, that is why you have this plus 1 as the charge. The charge you will say is plus 1. It is because of this plus 1 that Li plus ion is formed. So Li has a tendency of the effective nuclear charge to be equal to plus 1 only, क्योंकि अगर आप lithium atom को as it is लोगे, it will tend to form a compound, and whenever it will form a compound, there it will exhibit a plus 1 oxidation state only. ठीक है? Or yes, it is equal to the oxidation state, because if you talk about the charge on Li, it is plus 1. Okay? Difference between covalent radius and metallic radius. See, for that we need to discuss what is a metallic bond and what is a covalent bond first. What is an ionic bond? Ionic bond is the one which is formed by the complete transfer of electrons. जैसे NaCl, right? This is your previous classes thing. You have Na plus Cl. ठीक है? What is your Na? That is 3s1. It has one valence electron, and Cl is 3p5, right? 3p5 na? So it will have a tendency to take this electron up. So Na will completely give it, it will form Na plus, and Cl will completely take it, so it will become Cl minus. So basically this kind of a bond is known as an ionic bond or an electrostatic bond. Covalent bond is the one which is formed by the sharing of electrons. What is a covalent bond? It is formed by the sharing of electrons. And your metallic one is the one, again, when you talk of, it is the bond which is there between different metal atoms, where the metals are electropositive in nature. So basically if you talk about the structure of any metal, say sodium, so the sodium in itself is not just sodium. There are many other sodium atoms in it, contained in it. So you have a sodium and a sodium bond getting formed, and that's known as a metallic bond. Okay? And then when you talk about the radius will be half of the average of the length of the two, more or less, and we will discuss them in details in future. Then the next slide please. So remember that whenever we talk about the ionic radius was the question, whenever we talk about the ionic radius, remember that the radius of the cations will be smaller than that of the normal atoms, and the radius of the anion will be greater. So ionic radii is basically the radius that is calculated for this the radius that is calculated for the ions. There was a question that I think okay, and then we have, please give the answer, we have asked this many times. Can we say that the size of an ion is more because per electron effective nuclear charge is decreasing? See, in this case you say that the anionic size increases mainly because of the the nuclear charge remains the same, but you have the electronic charge now increasing because the negative charge is increasing. Clear to everyone? So in this case the nuclear charge remains this and the electronic charge is increasing. So because of that there are repulsions from the inner shell electrons, and the tendency of the nuclear charge to hold the outermost electrons is a little less than before, because of which the size expands. Okay. So now to just wind up, why transition elements show variable valencies is the last doubt for today. And transition elements, basically transition elements, I had taken up an example. Let's take up an example of titanium. What is your titanium? 22. What is that? 3D2 4s2, because 4s gets filled first, but when you write down the configuration I have told you to make sure that you write 4s outside. So it is 3d2 4s2. पहले electron किस में से निकलेंगे? Where will the electrons lose from? From 4s. So the configuration it can show +1, क्योंकि 1 तो जल्दी से देगा, s में से ही तो lose करना है, but it will be very happy to lose +2 electrons, तो +2 भी दिखाएगा. So one of the most stable oxidation states would be +2. Now for the next case, जब +3 शो करेगा तो +2 में it becomes 4s0, +3 शो करेगा तो it will show 3d1 4s0. So that will also be stable because it is looking for the argons configuration. So here it will have 3d1 4s0, and when it will show +4, now for +4 it will be 3d0 4s0. So the tendency to show variable oxidation states come in from the knowledge of your electronic configurations only, because our idea is to get first the valence shell either completely filled or the outermost shell to be completely filled. When it loses out electrons like this, you know, when it loses all the 4 electrons it will attain a noble gas configuration. So here it loses +4, and then plus 2 and other plus 1, plus 1, plus 2, plus 3 are also the other oxidation states which are possible. So that is why transition elements have this tendency. Now a quick recap of what we have done today. We have started with periodic properties. Atom साथ के साथ develop हो रहा था 1800 से. 1829 में the first arrangement of elements was done. That was done by Dobriner according to triad. Then thereafter you have thereafter Newland gave his law of octaves, and in between I give you some more names which and Cortois, and then we have forget, the first one was mainly by the ones which got recorded in black and white properly. The first one was Dobrina, the second was given by Newland, the third was given by Mendeleev. What does Mendeleev's law states? That the physical and the chemical properties are a function of atomic mass. Okay, and then came the modern periodic table, which was started to develop by Moseley, but because of the World War he had to just leave it cut short. So then the modern periodic law states that the periodic and the chemical properties are a function of their atomic numbers, and then we learn the periodic table, and then we just go beyond it, and from here your chemistry has just made a beginning. So from this point we'll just continue further and take up questions from it. I'm sure you all should be able to answer which is the most electropositive, which is the most electronegative, ionization energy, highest, lowest, and so on, questions like that. Be aware of all those questions, and then next time we'll take up questions directly from this much of portion. Okay, thank you.